Hello and welcome to the sixth lecture in my operating system development lecture series. Today I would like to talk about actually loading the kernel. So after this lecture, I will finally be able to talk about what really OSDev is all about, because all of the bootloader theory, that is not really relevant to operating systems all that much. I did present some concepts that one would often need in their kernel, which is why I won't have to talk about them that much in the future, such as the GDT or the general idea of paging. But still, nonetheless, finally, I'm going to be able to talk about the real OS stuff. So, firstly, I would like to do a little recap of what actually is going on. What is this high-level picture of an operating system? We have some bootloader, which is the first program that is initiated after turning on your computer. So the very first thing that an operating system does really is it launches its bootloader. And the goal of a bootloader is essentially, well, you have two main goals: to load the kernel, and since you're loading the kernel, which is in some specific format and has some specific requirements, the job of the bootloader is also, and that is the second thing that the bootloader needs to do, prepare an environment for the kernel to be properly functioning. So you have your bootloader, you have your kernel, and the general idea is that some part of this kernel is going to be some initial code or initialization code. So at the end of your bootloader, once everything is prepared, the goal is to somehow, by some means, start executing this kernel initialization code. In most cases, this kernel initialization code is a part of the kernel itself, and that's how most hobby OSs do it, and real operating systems as well, but this could be as well just a separate program. So then essentially what the goal of the initialization function is to load all the different things related to the kernel and we'll jump to the user space, which then gets to interact with the whole rest of the kernel. This is a very simplified picture, but it shows us the general idea of what we have to do right now. Our goal is to start executing some kernel code, to load our kernel and jump to some initialization instructions. That is fundamentally what we have to do right now. So, the kernel is some sort of executable, because, well, obviously it contains code that is supposed to be executed. And, well, if you're using some bootloader which is already available, which is, by the way, highly recommended, then you should simply follow the documentation of whatever bootloader you're using. So, what executable format should you use and everything. In fact, most bootloaders should just have documentation with full examples on how to load a basic Hello World kernel. So you really don't have to worry about this part too much if you're using a bootloader that's already available. But what if you wanted to improve on a bootloader that you're making yourself? Or what if you just want to know the theory of, well, how can you actually load a kernel? Well, first I would like to also probably do a recap. It's not something I talked about, but it's something I believe most people watching this are familiar with, and that is generally how executables are made and what executables are. So, fundamentally, when you have your code, your source code, some file, let's say .c, right? This is just text. This is fundamentally just plain text. It doesn't have anything special, and it's not understood by the computer in any way. This is just text, but it's supposed to be understood by a human, and you need something called the compiler. Now, the compiler is going to take that source code, and what it is going to output is, well, usually an assembly file. So what that really means is you have some source which can be independent of the hardware that it's in. It can be logical for a human to understand. It can be relatively simple. And what you end up with is a set of different instructions that have to be performed by an actual processor. Now, this way of writing those instructions that have to be executed is usually symbolic. It's usually mnemonic, which is why we call it assembly. And not just pure machine code. So we have some assembly file, and the program that is actually supposed to turn that file into something else. This can be a stem, by the way. It can be S, for a GNU assembler, it's usually .s. Doesn't matter. So we have an assembler, and now here things depend. Because it depends to what result you are expecting. However, it is safe to say that in most cases, what you're going to get out of an assembler is something called an object file. So, what is the idea of an object file? Well, an object file is very similar to an executable in a sense. So, an executable, as we might know, it's this file that contains pretty much just instructions for a computer to do. That is an executable. You can take those instructions and you can execute them. That's why it's an executable. Whereas if you just gave it a text file, it wouldn't understand what to do with that, and it would just be gibberish. Now, there are different executable formats, and that's because you could put that information about how those should be executed in some specific way. Usually, pretty much when you have an executable, the idea is to store some headers, store some important information about the CPU instructions, and then just store the pure CPU instructions. But I will talk about that a bit more later in the video. So we have our object file, and an object file is very similar to an executable, except it is generally made for sort of this relocation. So the idea is you can take different functionality, you can link it with different object files in order to get one executable. So it still might not have some details intact because of the fact that it is not a full executable yet, and it's supposed to be sort of agile in a sense that it can still interact with other object files in order to create this one final executable. So it can take multiple object files, or just one object file, it doesn't really matter. And the idea is you pass them to a program called linker. And the linker is responsible for actually taking those objects doing things with them, managing them in such a way that you can create one final executable. So let's say we have an ELF file of here. For ELF stands for executable and linkable formats. Well, those object files are still in ELF. We're sort of they have a couple of different parameters. Again, I'll talk about that later in this video. So that's the idea. You have your source code. It goes to the compiler. You have a mnemonic representation of what your code actually does in the CPU. Then this mnemonic representation, it's turned into the actual representation in some format that is still modifiable for the final executable, and then you can mix those, or you could not, and then you get this one final executable which the operating system knows how to deal with. Yeah, so that is pretty much this whole thing, right? But set of tools over here, the tool chain. Now, usually when you just write code natively for the operating system that you're using, this compiler, right, and everything, your whole tool chain is made for the same CPU architecture and the same operating system that you are programming in. However, this often can be not the case for operating system development. And that is because you don't want to compile these things as if, for example, they were Linux programs. You need to compile them to sort of pure x86 instructions that the CPU can understand without an operating system. So whenever you have a toolchain or a compiler, right, that doesn't run the result directly on what you compiled it on, and instead it's for some other specific purpose, you call it a cross toolchain or a cross compiler. Getting a cross compiler, for example, for just x86-64 ELF is very fundamental towards creating this proper operating system that isn't potentially ruined by this extra function. Yeah, and that ELF file, right? ELF is a very popular executable format, but it shall be addressed, and this is pretty obvious. And this is not a con of this format, just to clarify, because, well, pretty much every better executable format has that. This is not directly understood by the CPU, in the sense that if you just place an ELF file, if you were to flash it onto a disk, obviously it doesn't give you results. It's very easy for ELF files to make them work. However, if you wanted to just glue some code that you already have, like for example from your bootloader, and some ELF file, then it wouldn't necessarily work, because it's not just this completely pure set of instructions that are supposed to be done. Whenever we have just a file that contains pure instructions without any formatting, just things that you could literally flash on a disk and start executing, we call that a flat binary. Now, you would, if you wanted to, for example, right now, write an ELF parser or some file system driver to actually read an ELF file from a file system from some disk, then you probably wouldn't do it in assembly. So you would have to use C. And in that case, eventually you'll probably want to compile it to binary because you can't parse the ELF if you don't have an ELF parser. So you would have to make it a binary so that you can actually glue it, a flat binary, so that you can actually glue it and that it works properly. However, this solution, well, it might seem convenient, and or like completely starting out or just making the bootloader like one thing. It can be rational. However, flat binaries are generally not the best way to store executables and then to load things. They contain very little information about the program that you're trying to run. And this will usually end up being an inconvenience in the long term. So it's good to load things from ELF files. Okay. So, right, if you just wanted to add some C code that does something, you could get it for all of this, but fundamentally just at the end and make it a binary, and then you could just add it to your disk, jump to that address where you loaded that thing from the disk, and well, right, you can jump to your flat binary and it'll execute it from here, and the CPU doesn't care if this was written in C or if it was written in assembly. Um, so yeah, just make sure to do it with a cross compiler, and it should be fine. However, before loading the kernel itself, you probably shouldn't load. Okay. First, I'm going to talk about some file system considerations. So I keep saying that we want to load some information from a file. Like we want an ELF file, it will be our executable, we'll have some kernel.elf, and we want to load the kernel from that. But wait, kernel.elf is a file. Right now, from, well, the material that I have explained, I have not explained a file. I have not explained how we can sort of have a file because we have not implemented any file system. So our OS has no definition of what a file is and how it behaves. So there are some file system considerations that one could make, or rather, also the considerations of a lack of thereof. So, what are some approaches to loading a file, quote unquote? Or what I really mean by that is reading some information from a file. What are some multiple approaches to just generally doing that? Well, it's simply a file stored in a disk. It's fundamentally some data you have to read into the RAM, and then you can read from the RAM. But how can your disk layouts look? Well, one thing that you could do is you could have your bootloader code. So this is just, this flat binary, the bootloader code that is on your disk image. And what you could do is right after this boot image, right after all this boot code on your disk image, so you could append to this disk image simply the pure information, the pure ones and zeros stored in this file. So you could literally place the kernel.elf file, all of its data, right next to that. Then, if you had the location, and it's like totally possible to get, right? And I say this unironically, right? You can simply know where this ends when you load into the RAM, or you can know the position of this on the hard drive, or whatever disk you're using. And what you could do is you could simply jump to this address from the bootloader. And congrats, you would start indeed executing kernel code. So just like that, you would be executing kernel code. However, well, that is not a proper file system, but it is placing a lot of data and really calling it a file. One other thing that you could do is you could have somewhere on your disk an actual, let's call the proper FAT32 partition. Well, the file system here is irrelevant, but what matters here is you have some partition on your disk image of your operating system that actually is formatted in a file system that is supported, you know, that you would like to implement in your operating system. And in this partition, you would actually store your kernel file, so your kernel.elf. You could do that, and then you have two choices, two options. If you really don't want to implement a file system right now, you could just have this partition, but completely not care about the file system. You could just have some minimal code that would take this file without actually implementing the full file system and just set some very static values and to jump to this and start executing it from here. Well, you would first load it to the RAM, but the idea is the same. You jump to some predefined addresses, so you don't actually care about the proper structure of a file system. So this is definitely a solution, some solution, because, well, you have some disk image, you have a partition, you can put a file there, you can read a file from there, and you can sort of easily interact with it. However, this is still not a fully proper approach, because what you should do is actually make those drivers, well, I guess you can call them drivers, for interacting with a file system. Just implement file system support, and it's really not that difficult. It's really just a bunch of tables that are stored in file or just on the disk, and you have to sort of see how to parse them, get information from them. It's really not that difficult to implement a file system, especially something like Microsoft's file allocation table. And then you can properly read the file kernel.elf off the disk into the RAM, and then actually jump to necessary instructions. And this is the fully proper way to do so. So those are some file system considerations I just wanted to talk about because, well, our kernel is going to be some file, it's some executable. As it's a file, I wanted to mention this notion of a file system and potential ways one could deal with just getting this to work. Okay, so we get the general idea of what we are supposed to what we're supposed to do when we want to jump to some executable code. Again, the idea is to just have some source code compiled for a cross compiler, and then we either get a binary file, we glue it, and this is recommended if you're still writing a part of a bootloader. So if you're going to implement the ELF parser or the file system support, and it's still pretty much a part of the bootloader that tries to read the kernel, then sure, you can turn it into a binary through a cross compiler, and you can sort of glue it and just jump to that address. So it's very simple. And then if you actually want to do the kernel part, you should probably compile the kernel to an x86-64 ELF. And then we're going to parse that ELF file and actually to jump to where we need to. So that's the high-level idea. So I should probably start talking about the details of how to actually deal with an ELF file and what an ELF file contains. So ELF stands for Executable and Linkable Format. So, as the name suggests, it's a format for executables, and it's also a format for linking things. So this is, I'd probably say, the most popular if it comes to hobby operating system development. Most people choose this format. Some other formats were around. So ELF is used on Linux machines. If you have a Mac machine, it uses this sort of strange executable format called Maco. Windows, generally Microsoft DOS systems, they often use an executable format called COM. It was a very simple format, and some people still implement it just because of its simplicity. The idea is that it is pretty much a flat binary that you load into the address 0x100. So just 100 in hexadecimal. You load the contents of that address and you simply jump there, and all the addresses before that, they store a little table about what happens during the runtime of the executable. This might not be fully correct, because I'm not. I mean, the part about loading it into 100 and jumping to that's correct, but I'm not entirely sure what the table is used for. I'm pretty sure. I don't know. I think it stores some initial information about launching the file on DOS systems as well. I'm really not sure about what exactly this table can be used for, but it stores a table that is related to the program, but that is the important part. Currently, NT systems like modern Windows systems, they use a format called PE, or Portable Executable. It is used for files such as the exe files. It is used for DLL files, and I briefly mentioned PE in my, I believe, second lecture when I talked about booting. The actual file that is booted by the UEFI is just a portable executable. But we'll focus on ELF, or the executable and linkable format. So an ELF file generally tends to look like this. We first have, like any proper format should have, a header. We have the ELF header. After the ELF header, we have the program header table. I think I'm just going to write PHT for short. And PHT here just stands for program header table. I should probably rewrite that D. So we have an ELF header, we have the program header table, and then we have sections of the ELF file. So pretty much the most important section is .text. So .text is the section of the ELF file that actually contains the code, the executable instructions that are stored in the ELF file. That's your .text section. So you can encounter some other sections, for example, .data. And you can have those different ELF sections. There isn't a fixed number of them. in every ELF file. I can add one more. RO data, so read-only data, that is another valid ELF section. And then you can have your SHT, or section header table. So this is the layout of a general ELF executable. Well, not just executable, because again we've said that it can be linkable, so it's also an object format, and it can also be used for shared libraries and such. So the ELF header, it contains very general information about the ELF file. I'll talk about what exactly it contains in a minute or so. Then the program header table, it contains information about these different sections of the ELF file. So those sections, they just contain some sort of, ones and zeros, and we have to know how to interpret them. So if it's alt text, we know that we can execute this. If it's data, then we can't. It's something we have to store. We'll have a lot of information given to us about how exactly we should deal with this, or what can we do with this. And now the section header table actually does something extremely similar. It also describes the functioning of those sections. So why do we have a program header table and the section header table? And what is the difference between the two? The main difference, at least as far as I'm aware, is that the PHT is generally more associated and used in actual executable files. So when you have an ELF executable, what is actually going to concern us and what we have to care about is the program header table. However, when we're dealing with, for example, object files, we care more about the section header table. So that's the main difference. So that's the file itself. So that's just the file, the actual executable. But when we actually load it as you could pretty much call it a process. It's going to look slightly differently. Perhaps I should explain the difference between a program and a process. So when we have a program is something passive. So a program can be just a set of instructions, but it's laying on the desk, or it's there in the RAM, but is never to be executed. So this is your program, it's passive. And this over here is a passive structure. We just have a bunch of data, and we're not doing anything with it right now. It's just stored. This is something we can call a program. Now a process is an operating system concept of this becoming active. So it's an active element of the operating system. So I mean, this can be a little bit confusing because there are finished processes and ghost processes and zombie processes, but the general intuitive idea is that once we fully parse the program, once we start executing its code, and we have to sort of manage all the stuff that it's doing, then we call it a process. So a program to us is nothing but some collection of ones and zeros that might or might not be used, and then process is something we have to regularly take care of because it's trying to, take all the resources and actually participate in the functioning of the operating system. Now, processes are a bit more interesting to talk about when we're actually trying to make a process system, but we don't actually care about that right now. And that is because we just want to launch one process. We want to start executing our kernel code from this kernel executable. So I don't have to talk much about processes and generally how you would deal with creating processes and such in an in a proper operating system. I will talk about that in a later lecture. But still, I will give a general idea of how this program can map to an actual process and how its memory layout can look. So this is our ELF file, and when you have your actual memory, you probably have just your code. So code is just anything that was flagged as executable, and it's put together, and it's supposed to be executed, jumps to each other, does all these different things, and it just uses the CPU time in order to perform different operations. This is your code, and you're probably just going to map things like text to it. Then, I mean, realistically speaking, you might, for example, have some blank space or whatever. You have your data. For example, this can be data, this can be the read-only data from the ELF file. And then this is something that for sure is not going to be in the program itself, but it has to be in the process because it's just unnecessary to store. Well, you have to reserve some memory for the stack. So memory gets its, I mean, a process gets its own little bit of memory as well. That is the stack. You can store information here, and if it runs out of possible information it can store here, then it can allocate more memory from what is outside of this process memory. So it can do that with memory allocation, but it's also a topic for a different lecture. Okay, so yeah, we have our stack. I mean, processes can also store different things. You can have process control block and everything. That doesn't really matter to us. But what we at least want is some mapping of, well, code, data, something. We want to place these things per file to our memory and then actually start executing that. And in order to do that, we have to understand this format and what is generally stored a bit more. So first, I'm going to talk about the ELF header. So the ELF header, it's at the very beginning of the ELF file. And I'm going to present the 64-bit version. The 32-bit version differs a little bit, so if you are writing something that is 32 bits, you'll have to look that up. The differences are small, but they are there. So I am going to index the bytes in the ELF header from 0, and I'm going to say that first 4 bytes from 0 to 3, it's the ELF signature. ELF signature, first it's the magic number, which is 7F in hexadecimal. So this should be the first byte of your ELF file. Then you have ELF, simply stored in ASCII. Then you have the information about whether this ELF file is 32-bit or 64-bit. So if this byte is 1, this corresponds to a 32-bit executable. 2 corresponds to a 64-bit executable. And what we really want is this. So if it's not this, then something went wrong. Then you have the endianness. So if you have 1, this means that it's little endian. If you have 2, it means that it is big endian. Then 6 is the ELF header version. And one thing to notice here is this is not the ELF version. This is just the version of the header itself. Yes, it was, I guess, might be important if you're trying to see if it's not using some deprecated format, but generally it's okay to ignore, I guess. Then the operating system ABI that is used, again, we don't really care about that. Then 8 to 15 are unused, very sort of padding. And then 16 to 17, actually interesting because it tells us what the type of the ELF, what type of ELF file is this? And so the first type it can be, the one, is relocatable. And this is just a fancy name for an object file. So if, one, it means we're dealing with an ELF object file. Two means that this is an executable file. And again, this is something that we want because we're trying to load an executable, so it really shouldn't be anything else. Three, that is a shared library, shared object. And four is a core. So like if it dumps a core, if it's creates a sort of save of the program and save, then that can be stored in ELF, and then this will be 4. Again, we really just want this to be 2. Then 18 to 19 is the ISA. It's what CPU architecture we are going to be dealing with, and as I've pointed out numerous times in this lecture series, this is dedicated for x86 CPUs. So really only 2 values interest us. If it's 3, or hex 03, then it corresponds to x86. So it's going to be x86. However, if it is 0x3e, so 3e in hexadecimal, this actually corresponds to x64. So if we want to implement support for 32 bits executables, or if we want to check if something went wrong and then compile for x64 or something like that, then we could check this. But yeah, these are the only 2 values that could potentially interest us. Then 20 to 23 is the actual ELF version, the ELF header version. And yeah, that is some very basic general information, right? Is this 32-bit or 64-bit? What is the architecture? What kind of ELF file is this? What OS ABI does it use? The different versions, the endianness, all the and the signature, right? All the stuff you would generally expect from some format header. But then it becomes pretty interesting from point number 24 with indexing from 0. And that is because 24 to 31 is the program entry offset. So again, we get 8 bytes in order to say what sort of address, right? So we get 8 bytes, so 8 times 8, that's 64 bits. So we get a 64-bit address that tells us where our program entry is. And that is very, very important, because this is the address that we want to begin the execution of our program at. Then 32 to 39 is also an offset. It's the program header table, or PHT offset. So obviously we will want to read from the program header table, and in order to do so, we obviously have to know where it is, because what we'll do is we'll take a look at the program header table. It will contain different information about what should be loaded, where it should be loaded, do all those things, and once all the sections are properly managed, then we can jump to the previously specified program entry offset. And this is fundamentally how ELF is going to work, right? So we're going to iterate through this program header table, manage all the sections defined in the program header table, and jump here. So then 40 to 47 is our section header table offsets, which we don't really have to care about for our purposes. 48 to 51 are the general Unix flags, where I can just say flags, but they follow Unix standard permissions, standard flags that you would have on Unix-like systems. So as you might know, when you have Unix-like systems, they generally have 3 attributes, 3 sort of permissions, 3 sort of security flags, and that is read, write, execute. And they're usually just written in the form of 3 different bits. And because of the way the binary works, right, this read is going to correspond to the value 4, because it's 2 to the 2nd power. This is the write permission is 2, because it's 2 to the 1st power, and x is 1, because that's 2 to the 0th power. And you can sum those, right? So if you've used Unix-like systems, if you've used Linux permissions and attributes, you're surely familiar with converting this read, write, execute to numbers, because, for example, when you make create directories, and you would have something like rwx -x, right? And you want to set a directory with those permissions. What you do is you can simply use the code. So this is 4 plus 2 plus 1, that's 7. 0, 0, and then a 1. So that's 1, 0, 0, and a 1, 1. So you get 7, 1, 1 as your code. And yeah, so that's the flags, and this is exactly the format that those flags are stored in. So in the ELF file, we have the permission stored as so RW and RWX. So for example, if this was 6, this means we have read and write permissions. If this was 7, read, write, and execute permissions. If we have let's say 3, that means, or let's say 5, that's a read and execute. I think that's pretty simple. Well, your exact implementations of how you deal with those flags, it's up to you. Generally, if you're going to make a Unix-like system that deals with those Unix flags, then the general way that Unix-like systems enforce it is that the most rigorous flags that it finds are the ones that are enforced. I'm saying this because we're going to see flags in the program header table, and if you're going to read at some point the section header table. So this might be important that if you want to follow the standards, then you want to enforce the most rigorous flags. So then 52 to 53 is the size of the ELF header. Then 54 to 55 is a size of a PHT entry, so the program header table. So in bytes, how much does one entry take up? And then 56 to 57, it stores the number of PHT entries. And then 58 to 59, it stores the size of one section header table entry. Again, we won't have to care about much about that one. 60 to 61, right, that's the number of SHT entries. And to finish this off, so we have 64 bytes in our ELF header. We have a section index to the SHT. Or not VSHT, or the string table. So what really interests us from this is, well, potentially the flags, if you want to implement them. They're a bit more important when you actually load processes from more ELF files that are actually supposed to run on your operating system and not just be your operating system. So what really matters to us is, well, where is our program header table? What is the size of one entry? What is the number of entries? Because we'll need that to perform this iteration, and to actually properly deal with those ELF sections. And once we have dealt with those, we can jump to the program entry offset. So these are the information, the source of information in the ELF file that we care about the most. So, what is stored in the program header table? Okay. So, let's say we have the offset of our PHT, and we know the amount of entries, and we start reading the first entry, or any entry for that matter. What will we find here in a 64-bit file? Well, typically what you'll find first is the segment type, lines 0 to 3. So this is the segment type, and if you find a 0 there, it means you should simply ignore this section. Ignore this segment entirely. You don't want to care about it. So this is ignore. Then 1 is the standard. I'm just going to call it STD for now, and I'll elaborate on what that means exactly later. 2 means that this is dynamic in the sense that it requires dynamic linking. 3 means that it's a path to an executable for a potential interpreter and such. And then 4 means that this simply contains nodes. So what we're really hoping for most of the time is that this is just a standard segment. So in 47, we have the flags. And again, they're the same flags that were in the header previously. And if you want to actually implement flag support, you would do so by enforcing the most rigorous flag that you find. This means that if these flags are more rigorous than the flags in the elf header, then you're going to use those. However, if those are less rigorous, the elf header flags, then you don't just magically start using them for this section. Instead, you enforce the more rigorous ones, which are the ones from the elf header. Then 8 to 15 defines the actual offsets of where you are supposed. No, this is the offset of where in the elf file can you actually find. This is the offset from the start of the elf file. Where can you actually find this section of the elf file? Then 16 to 23. This stores the virtual address that this is supposed to be loaded in, right? And we're currently in virtual address space because we set up paging. So this is good. Now we can now properly say that we are indeed loading it into a virtual memory address. So then also the physical address will be stored, but that is not really important. At least for our purposes. 32 to 39, it's going to contain file size, which pretty much this is just the size of this section inside the ELF file. So using these two values, you can pretty much determine where does the section begin, where does, all the zeros and ones that are supposed to be in the section, where do they begin in the ELF file, and where do they end? So the point of when they begin, starting from the start of the ELF file, that is your offset, right? That is your offset. You will add your offset to the first, where you have loaded your file, and you'll get your section. Then if you add the file size, which is in bytes, then you'll get the end. This is how much does this actually take up in the file. And then 40 to 47 is the memory size. So what should be the size of the actual memory that you reserve for putting that in? And I'll also clarify that in a moment. And then 48 to 55 is required alignment. Required. Yeah, required alignment. So that is because there are some alignments, like for example, some programs have to be page aligned and such. This will usually be a power of 2. This is a required alignment of this. So we have a standard file, right? It doesn't need dynamic linking. It's not notes. We're not supposed to ignore it. How do we deal with this? How do we just use these values to actually do something? So like I've said that we have to iterate through the program table. What do we actually have to do for each of those sections? Well, what you have to do is you have to clear. You have this value, memory size, right over here. And at the virtual address that was specified, So we have our memory. We have some virtual address that was specified. And over here, you should reserve or just reset to 0. You should clear some memory for where we're going to place this section. And just about how much you should clear is dictated by the memory size over here. So this is the memory size that starts at the virtual address. So this is how much you should clear, how much you should set to zeros in your memory for this. Once you have that, you should take the offset of where the section is in the ELF file, and then you should read file size bytes from this offset and load this many bytes into this virtual address. So you have some offsets, right? So you have your ELF file. It starts somewhere. You add the offset. You have your section. And what you do is this has, right, file size. And this is how many bytes, starting from this offset, you should load into the virtual address specified here. And usually you're going to have a bit of leftover of cleared memory. And this is actually intentional. The memory size and file size should be different. And well, it makes more sense when you actually have processes, because, and this is optional space, but it could be used for different information about the process. Yeah, so that is the general idea of how you should treat this. So from the start of the ELF file, you have the offset, right? You have your section, and you copy file size bytes. You move them right over here from this offset file size bytes into where the virtual address is, and make sure beforehand you cleared or reserved or whatever memory size of bytes out of this virtual address. And then right afterwards, you should have another entry of a size specified in your ELF header. Yeah, and this is basically how to deal with a PHT. So once you've dealt with the PHT, you can simply jump to the offset that was specified in the ELF header, the program entry offset, and you should start executing kernel code. And this is a fundamental idea of how you can load kernel. So again, what is a potential strategy of how you can load a kernel? Since you probably don't want to make an assembly, right? You have your code in assembly, you have your bootloader. What you do is you compile some stuff like Filesystem support or ELF parsing written in C to a flat binary through the linker and everything, and a cross compiler to x86-64. You make a flat binary. You jump to that. By glue, by the way, this is a very colloquial term. I mean, append to the disk image. Then you just, once it's read, right, because I talked about reading the disk, so now it's in the RAM, you jump to the RAM address where it was loaded, and then you can actually, for example, use the file system in order to see where the file is, and then parse the ELF with the ELF parser, jump to the program entry offset, because the kernel was previously compiled to an ELF. It was placed in the file system. So now you can jump to it, and congrats, you have jumped to kernel code. And now you're probably executing a kernel. So that's the fundamental idea of loading, and I think this lecture is generally useful because, well, it would feel empty without a lecture on how to load the kernel. but it still introduced a lot of concepts about just generally linking, loading, dealing with all those things, and I think that is very important to be comfortable with if you want to do operating system development. So I hope that I have, this is everything that I wanted to talk about in this video. It's a bit of a shorter video. I hope that I have clarified some things about loading the kernel, and finally, in the next lecture, I'll be talking about actually writing the kernel. So, one could say that we will finally get to it. Thank you very much for watching, and I hope that you'll watch the next lecture.